Hello everybody, my name's Ben Burgess. I work for an engineering company called Bureau Happold Engineering, and I run the acoustics engineering team for Bureau Happold. So I'm going to talk to you a little bit about some of the main considerations that we look at when we're engineering the acoustics in performance spaces. And I'm going to talk about a case study, about one project example, which is the new concert studios for the BBC in London. And that is a development where there's orchestral music, there's rock and pop, and there is performance as well as recording. So I'll share my screen. If I'm talking too fast or you don't understand what I'm saying, please feel free to interrupt me, ask questions, say slow down, repeat it, no problem at all. Let me know how I can make it more easy for you. This is a little overview, first of all, of the performance studios for the BBC. And if you can't see my mouse on the screen, let me know. But this upper volume here, this big space at the top, is the orchestral performance and recording studio. And this is where the BBC Symphony Orchestra and the choir are going to rehearse and record and perform. And then in the basement, underground down here, is the rock and pop studios for the BBC. And this is where all the bands and live acts are going to record and perform down here. So these are our adjacencies, the rooms which are next to each other, which are very, very sensitive. And what the most challenging one is this guy here, because we have the orchestra on the upper floor, and we have rock and pop just below them on the floor below. So we need a very, very high level of sound reduction between these two spaces. And a little bit about the kinds of things that we look at when we are designing the acoustics of a development. One of the first things we look at is what we call noise break-in. And this means noise from outside the development getting inside the development. And it can be from things like aeroplanes, cars, rail, underground lines. And this means that we have to design the outside of our building to be very acoustically robust so that external noise doesn't come in. And that affects things like the external facade, the windows, the roof, those kinds of things. And a very simplified version of how we calculate this is that we take the outside level, the level of noise outside the building, and we know the level of noise we want inside the building. And if it's for performance, it's going to be a bit higher than if it's for recording. Because if we're recording, then if any external noise is audible on that recording, if you can hear it, then that's a problem, right? Because when we listen to our our Spotify recording of our favorite band or whatever, then if it has traffic noise on it, if we can hear the cars on the recording, it doesn't work. And so if we knew that the outside level was 70 and the inside level had to be 40, we know that we'd need to reduce that by 30 in order to get the performance we want. And so that's what we would apply to our facade. And we also consider distance attenuation too. An example of what we had at the BBC studios is that actually the BBC's own truck, which is shown here, generates very high levels of noise. And that goes past the building, and there's a window up here into the concert hall. And so what we had to do there was think about the low frequency noise that comes from the engine of the truck. And we had to design the window to be very thick and very robust, so that it reduced the noise of the engine coming through into the recording studio. The next thing we look at and we think about is noise. Oh, sorry, let me just go back. I know that your site that you're looking at is near some major roads and also some industrial units. So that might be something that you want to think about in terms of the noise breaking into your development. What about the noise from the roads? And what about the noise from the industrial units? And also, I think there's a power station too. So all those things could be very noisy outside on your project. The next thing that we look at is noise breaking out of the development. And this would be, the noise from the bands or the DJs breaking out through maybe the windows and impacting on noise sensitive properties nearby. And by noise sensitive, we mean things like houses or schools or hospitals. Anything where noise is going to disturb people, then we have to think about how much noise is going to impact on them. And at the BBC, we had next door on the left-hand side here is a college, and on the right-hand side, this is a theatre. So we had to think very carefully about how much noise was going to break out of our building and disturb the neighbours. And that might be something that you think about on your site. I know there's a church nearby, so maybe if we're planning high levels of music noise from gigs or DJs or bands, then we might want to think about how much of that noise is going to impact on our neighbours, like the church and things like that. The next thing that we look at is called sound insulation, and that's how much noise transmits from one room to another room. And that's really important if we have more than one space in our development and more than one noise sensitive space. So let's say that we have one space for performance and one space for recording. It's really important that the noise which is generated by the performance doesn't get into the noise. It doesn't get into the room where we're recording the noise for the recording, because then you get, both bands end up in both rooms. And for sound insulation, it's quite common sense. If we have something like a store next to a toilet where the acoustics are not really important, we can use quite a small partition, quite a small wall, and it can be quite light materials. But if we have something like a music practice room next to another music practice room, then we're going to want to make that much bigger and use much heavier materials so that it stops more sound on the way through. When we have very high performance music developments, what we tend to do as engineers is build something called a box in a box construction. And you can see that here in that what happens is that we put our band inside one structural box, and then that sits inside the primary structural box outside of this. And what that means is that it's much more difficult for noise to be transmitted between different spaces, because there's an air gap between the performance or the recording space and the next space. At the bottom, we have to support it somehow. What we actually do there is usually support the box on a line of springs. And then what that means is that as the sound goes into the structure, it turns into vibration, and some of that vibration is lost in the movement of the springs. The next thing we look at is called room acoustics, and that's how much sound bounces around the space. We can think about it as echo. And if we think about a cathedral or a big cave, that feels acoustically cold, and your bedroom at night probably feels acoustically warm. And that's because the cave or the cathedral has only hard surfaces, and it's a very big volume. So that means that the hard surfaces reflect the sound around the room. Whereas in a bedroom, we have curtains, we have carpet, we have the bed, and those things are soft, which means that they absorb the sound and the sound doesn't get bounced around the room. And the balance between those things is what people call good or bad acoustics for performance spaces. So when people say, oh, I went to a gig and the acoustics were amazing, that means that the sound is being bounced around the room to just the right level. We don't want it to be too high, because then it's quite confusing. We don't want it to be too low, because then it sounds dead. So finding somewhere in the middle is perfect. An example of how we do that in a concert hall scenario is shown here. So we have somebody performing here on the stage, And if we take this audience area, some of the sound is going to travel from the performer straight to the audience. And some of the sound is going to be directed to other parts of the space and be bounced back towards the audience. This orange line will take a lot longer than the blue line. And if sound arrives from the orange line at the same time as the blue line, it's going to be very confusing to the people who are listening, because they're going to hear different notes at the same time. And so what we do in this example is we would make this yellow area here an absorbing material, so that when the sound hits it, it doesn't bounce back. The spaces around the performer, we would make a hard reflective material, so it pushes the sound out towards the audience. And here are some examples of different sound absorbing materials. They can be soft wall panels that can be stuck onto the walls, or they can be hidden behind like a timber screen. And normally in this example here on the left, there's a soft material which is hidden behind the timber, so it looks like it's wood, but actually there are holes which sound can leak through and be absorbed by the material behind. The next thing we look at is building services noise, and this is noise which is generated by the ventilation and heating systems. So we don't want to go to a gig or be recording any music and be able to hear the noise from fans or from radiators or any kind of services noise. So it's important that that's minimized. And the way that we do that is by including what we call attenuators on our air movement ducts. So this is an air handling unit. It's a big fan which is pushing air into the building so people can breathe. And we have 3 lines of attenuators which reduce the noise from the air before it gets to our recording space. And this is what an attenuator looks like in reality. And it's just a tube, and this is this inside has holes in it, and some of the sound as it moves through will go through the holes and be absorbed by this foam which is in the core of the material. The final thing we look at is the sound system design. So that's the performance of the speakers, sometimes even the screens. And that's really important to performance, because as well as the room acoustics, how the sound is bounced around the room, the performance of the speakers is what you enjoy, what you perceive. So that's really important too. And just a couple of examples of where we've done this kind of thing in real life. This is a big venue in Manchester in the UK, and it's like a warehouse type venue. And this wall here at the back is actually a glazed external wall, and on the other side there are some apartments. So we had to make that wall very, very, very high performance to prevent noise from in the warehouse breaking out and disturbing the people in their apartments. Some people might recognize this one. This is the Glastonbury Festival. Here we will be looking at the loudspeakers, which are shown to the left and the right of the stage. And it's about orientating, about angling the loudspeakers so that they impact on the most people in the crowd and that people have an amazing experience once they're there. This is another famous venue, the Royal Albert Hall in London. And this was again about the loudspeakers. They recently replaced all the old loudspeakers in the venue, and we advised them on where they should put the loudspeakers, which angle they should face so that most people can enjoy the sound. And this is a big arena in China that we just finished designing, and this is about preventing the noise from in this arena from being transmitted vertically upwards to other parts of the development, because above this arena there are apartments. And so when there's a performance on in the arena, it's really important to make sure that the people in the apartments don't hear it, because they might be sleeping or working or resting or whatever. And this is a theatre. So also, you know, acoustics are really important in theatres as well, because people need to be able to hear the performers. If you can't hear the speech, if you can't understand what they're saying, then you're not going to understand. Then you're not going to appreciate the performance. This is a music hall that we did recently, again in the UK. This one, and this is about providing a very, very beautiful recital room for orchestral music, and it's about mainly preventing. You can see that there's a concave, a curved shape to the back walls. The challenge with that is that if sound hits a concave shape, it can focus it like a lens in a microscope or a telescope and focus the sound into one point. And so you can see on the back here that we've used a very textured wall finish, so it's very uneven, so that the sound is bounced around evenly all over the space. And this is the most recent job we did. This is the Spotify headquarters in Germany, in Berlin, and they also have bands and gigs in their offices, and they have quite a lot of people in this space, so they need to push in enough fresh air so people can breathe. But we also had to check that the noise of that air being pushed in by the fans didn't spoil people's enjoyment of the gigs that they had in the space. So that's my presentation. I'm very happy to take any questions if anybody has any. Otherwise, yeah, hope you have a great time designing your project, and let me know how I can help.
Thank you, Ben. It was really interesting to hear everything. So I hope we will have possibility to meet you in process. Yeah.